What's up, everyone? Today we're going to be learning about the Fiat-Shamir transform. At a high level, the Fiat-Shamir transform takes an interactive proof system and turns it into a non-interactive one. This turns out to be a really important building block on our journey towards understanding zkSNARKs. So why does this matter? Well, in future videos, when we start building zkSNARKs, we will usually begin by designing proof systems in an interactive setting. Interactive proofs are often much easier to reason about and analyze. But on their own, they don't qualify as zkSNARKs, since if you recall, the N in zkSNARK stands for non-interactive. This is where the Fiat-Shamir transform comes in. It gives us a systematic way to convert those interactive proofs into non-interactive ones. In other words, it's the tool that lets us take something we understand well and turn it into something that actually works as a zkSNARK, which, as I've mentioned in earlier videos, is exactly what we want for blockchain applications. That's why it's so important for us to understand the Fiat-Shamir transform before diving deeper into zkSNARK constructions. Now, as usual, let's talk about the prerequisites. I'm going to assume that you've been following along with the ZK series so far. If not, I'd recommend going back and watching the earlier video where we introduced proof systems and defined what a zkSNARK is. On top of that, for this video in particular, it's important to be comfortable with elliptic curve groups. If that sounds familiar, you're good to keep going. If not, I'd suggest checking out my other videos on that topic before continuing here. Alright, if you're ready, let's get started. Now, today's video is all about the Fiat-Shamir transform, which is also often called the Fiat-Shamir heuristic. As we've mentioned before, this is the technique that lets us transform interactive proof systems into non-interactive ones. So let's start by recalling what an interactive proof system looks like. In an interactive proof, we have two parties, a prover and a verifier. They send messages back and forth over several rounds, and then at the very end, the verifier looks at the entire interaction, runs their verification algorithm, and decides whether to accept or to reject the proof. Now, what exactly are these messages that are sent back and forth? Let's first focus on the messages sent from the verifier to the prover. In many proof systems, we can design things so that the verifier's only real job during the interaction is to generate randomness. In each round, the verifier samples one or more random values and sends them to the prover. This randomness is crucial because it prevents the prover from cheating by choosing those values themselves. This brings us to an important definition. We call a proof system a public coin interactive proof if throughout the interaction, the verifier only sends randomness to the prover. That's all they send. After the interaction is done, the verifier then runs a verification algorithm and decides whether or not to accept or reject. This is important because Fiat-Shamir only applies to proof systems with this structure. So to summarize, what Fiat-Shamir tells us is that assuming that we can treat cryptographic hash functions as random, any public coin interactive proof can be converted into a non-interactive proof. Visually, you can think of Fiat-Shamir as taking an interactive back and forth protocol and turning it into a single one-shot proof. In picture form, we turn this into this. With that intuition in mind, let's see how this actually works by walking through an example. As our running example for understanding the Fiat-Shamir transform, we're going to use the Schnorr protocol, which is a very famous and widely used interactive protocol. You may have heard of Schnorr signatures, which are used in some cryptocurrencies like Bitcoin. That signature scheme is derived from the Schnorr protocol, hence the name. I won't be going into the signature scheme itself here, but after watching this section, you should be in a great position to read about it and understand how it works. So let's start by looking at the Schnorr protocol itself. The goal of this protocol is for a prover to convince a verifier that they know a scalar W, such that W times G equals H. Here, G and H are elliptic curve points, which is why I'm capitalizing them. They live in an elliptic curve group of large order. In fact, G is a generator of this group. Let's denote the order of the group by Q. Now, this group order Q is really large, typically on the order of 256 bits or more, depending on the security level we want. That means the scalar W is an integer modulo Q, so it could be any value in the range 0, 1, 2, all the way to Q minus 1. To make that concrete, if Q is a 256-bit prime, then Q minus 1 is a number on the order of 2 to the power 256. That's a number with roughly 77 decimals. In other words, there are an enormous number of possible values for W, and only one of them satisfies the equation W times G equals H. Finally, just to be clear, all of the group parameters G, H, and Q are public information and are known to both the prover and the verifier. Now remember that given G and H, you cannot easily solve for W. That's because of the hardness of the discrete log problem in elliptic curve groups. Hopefully that's familiar to you. If it's not, I recommend reviewing my earlier video on elliptic curve groups before moving on. Just to make sure we're all on the same page. So we have an elliptic curve group with a large order Q and a generator G. There's another point in the group, which we call H. The prover's goal is to convince the verifier that they know a value W such that W times G equals H. Both the prover and verifier know G, H, and Q, but only the prover knows W, which is a secret. So how does the Schnorr protocol actually work? Let's walk through it step by step. First, the prover samples a random scalar R from 0 to Q minus 1 and calculates U equals R times G, which is another point in the elliptic curve group. The prover then sends U over to the verifier. Next, the verifier samples a random scalar C from 0 to Q minus 1 and sends it to the prover. Once the prover receives C, they can compute Z equals R plus C times W. Since R, C, and W are all scalars in the field, Z is also a scalar. The prover then sends Z to the verifier. Now the verifier checks whether Z times G equals U plus C times H. This is the verification algorithm. If this equality holds, the verifier accepts. Otherwise, they reject. Notice that the verifier has all the information needed to perform this check. They know G and H from the beginning, they generated C, and they received U and Z from the prover. So why does checking Z times G equals U plus C times H actually verify that W times G equals H? Let's break down the math. I'll write it down and you can pause the video for a second to convince yourself that this is true. As you can see, if the verification equation Z times G equals U plus C times H holds, it's mathematically equivalent to confirming that W times G equals H. But here's the important question. Could a malicious prover cheat if they don't know W? They might try to guess a Z that satisfies the equation, but remember that Z equals R plus C times W. A dishonest prover only knows R and C, not W. Since W could be any value in a huge field of size roughly 2 to the power 256, the probability of randomly guessing the correct Z is astronomically small, basically zero. That's why the protocol is secure. At this point, we can also see why the Schnorr protocol is a proper proof system. First, completeness. An honest prover who knows W will always convince the verifier because if W is correct, the calculation of Z guarantees that Z times G equals U plus C times H. Second, soundness. A malicious prover who doesn't know W has an astronomically small chance of guessing a valid Z, so the verifier will almost always certainly reject. So since it satisfies completeness and soundness, this is a proper proof system. Even better, on top of that, this protocol is zero knowledge. The verifier only sees U and Z, and whether the prover passes the check or not. They never learn R, and more importantly, they never learn W. Even though the verifier knows C and Z, the hardness of the discrete logarithm problem means that they cannot recover R from U equals R times G, and without R, they can't solve for W from Z equals R plus C times W. More precisely, this protocol is honest verifier zero knowledge. That means it's zero knowledge as long as the verifier is following the rules. In this case, actually choosing the challenge C uniformly at random. So far, we've seen that this is an interactive proof system. Why? Because there's back and forth communication. The prover first sends U to the verifier, then the verifier sends the challenge C, and finally the prover replies with Z. This kind of three-message interaction is very common in proof systems, and it actually has a name. It's called a sigma protocol. Apparently the name comes from the way the arrows in the interaction diagram look like the Greek letter sigma. I'll admit, I don't quite see it either, but that's the name. It's also important to note that this is a public coin interactive proof system. Again, like we said before, that means the verifier's only role during the interaction aside from running their verification algorithm at the end to decide whether to accept or reject, is to generate a random challenge C and send it to the prover. And here's the exciting part. Because this is a public coin interactive proof, we can use the Fiat-Shamir transform to turn it into a non-interactive proof. Let's see how that works next. Okay, let's visualize what's happening here. On the left, we have our interactive proof, and our goal is to turn it into something like what you see on the right, a non-interactive proof. As a quick refresher, notice that in a non-interactive proof, there's only one message, and it goes from the prover to the verifier. That message can have multiple values in it, but the key rule is the prover only sends one message one time, and that's it. Now, you might be wondering, why don't we just let the prover choose C instead of having the verifier choose C? Then, in a single message, the prover could send U, C, and Z to the verifier. At first glance, this seems convenient, but let's check if it's actually secure. Suppose the prover is dishonest, and they try the following. They pick a random Z, pick a random C, and then they solve for U using U equals Z times G minus C times H. Then they send U, C, and Z to the verifier. When the verifier checks Z times G equals U plus C times H, it passes. And notice, the prover never actually needed to know W. This shows the problem. If the prover gets to choose C to be anything that they want, they can forge the proof. So right now, we have two competing demands. On one hand, the prover needs to be able to produce C, so that we don't need the verifier to send it to the prover in order to satisfy non-interactivity. On the other hand, we also need to make sure the prover can't just choose any C they want for security. This is where cryptographic hash functions come to the rescue. Assuming the random oracle model, we won't get too deep into that here. A cryptographic hash function, like SHA-256 or Ketchak, has a special property. Whenever you put in any input, though it's deterministic, it produces an output that appears random and unpredictable. Here's the basic idea. In the interactive protocol, the verifier normally picks some random value and sends it to the prover. In the non-interactive version, the prover generates that value instead. But here's the important part. The prover can't just pick any value they want. The value has to be determined by everything that happened earlier in the protocol. In other words, it's a cryptographic hash of the transcript so far. By the way, when we say transcript, we just mean all the messages and values that have been exchanged up to this point. By doing this, the output behaves like a random value, thanks to the properties of the hash function, so the output is out of the prover's control, so they can't cheat. Let's see how this works for the Schnorr protocol. To recap, in the interactive version, there's a step where the verifier generates randomness and sends it to the prover. To make the protocol non-interactive, we have the prover generate that value instead, but in a controlled way. Specifically, the prover must compute it as the cryptographic hash of the transcript so far. So what exactly is a transcript at this point? What do we mean by everything before? Well, in the interactive protocol, the prover has already sent U, so that definitely counts. It's also really important to include the public parameters that everybody knows from the start. So in our case, that also means G and H, because both the prover and verifier know these values before the protocol begins. So putting it all together, the prover now calculates C as the hash of G, H, and U. The specific hash function, for example, SHA-256 or Ketchak, would be agreed upon by the prover and verifier ahead of time. Once the prover has computed C, they continue with the protocol as usual. In one message, the prover sends U and Z to the verifier, which is the proof. Notice that now the verifier doesn't send anything to the prover. Once the verifier receives this message, what do? In other words, what does the verification algorithm look like now? The verifier's job is slightly expanded. Before checking the usual Schnorr equation, Z times G equals U plus C times H, they first need to compute the challenge C themselves. Since the verifier already knows G and H and receives U as part of the proof from the prover, they can compute this hash themselves. Then they use this value of C when checking if Z times G equals U plus C times H holds. This step is crucial for security. If a malicious prover who doesn't know the secret W tried to cheat by picking an arbitrary challenge C instead of computing it honestly as the hash of the transcript, then the verifier's computed C would almost certainly be a different one. As a result, the equality z times g equals u plus c times h would fail and the proof would be rejected. Because of this, the malicious prover is forced to derive C as a cryptographic hash of the transcript to have any chance of passing. But once C is fixed in this way, they can no longer work backwards to choose a convenient U, since the output of a cryptographic hash function is essentially unpredictable, so the prover just doesn't get to control it. I encourage you to pause the video and convince yourself of this. If you pick random values z and c, and then define u equals z times g minus c times h, like we did before, the hash of ghu will almost never equal the c you picked. On the other hand, if you start with the valid u and compute c correctly by hashing, then producing a corresponding z that satisfies z times g equals u plus c times h, while also matching that hash, would require solving the discrete log problem or predicting the hash output, which are computationally infeasible. So this construction is secure. In a nutshell, what we've done is replace the verifier sampling a random value with the prover computing that value as the hash of the transcript. The verifier simply checks that the prover did this correctly by recomputing that hash themselves before checking the Schnorr equation. This is exactly how the Fiat-Shamir transform turns an interactive Schnorr proof into a non-interactive Schnorr proof. Now, a quick recap of the interactive Schnorr protocol. There are 3 messages passed, first from the prover to the verifier, then from the verifier back to the prover, and finally from the prover to the verifier again. But what happens if our interactive proof system has more than 3 messages? How do we apply Fiat-Shamir in that case? That's the next question we'll tackle. For example, the Schnorr protocol is designed to prove a very specific statement, that the prover knows a secret W such that W times G equals H. By itself, that's all Schnorr can do. It can't directly express more general statements. But in this video series, we want to go further. We want to be able to prove arbitrarily complex computations. To do that, we'll need interactive proof systems where many messages are exchanged back and forth between the prover and the verifier. So the natural question becomes, how do we use Fiat-Shamir to turn these more complex, multi-message interactive proofs into non-interactive ones? The basic rule of thumb is simple. Every time the verifier would normally generate randomness and send it to the prover, we instead have the prover generate that randomness by hashing the transcript. And remember, at each step, the transcript means everything that has happened in the protocol so far. So for example, if we have something like this message will be replaced by the prover hashing these messages above. And this message will be replaced by the prover hashing these messages above. During verification, the verifier will then need to compute all these hashes themselves and then use the resulting values in the equality checks to keep the prover honest. And that's it. That's the core idea of Fiat-Shamir for multi-round protocols. The prover replaces the verifier's random sampling with hashes of the transcript, and the verifier just verifies that everything lines up by recomputing these hashes themselves and plugging these values into its original verification algorithm. Let's quickly recap what we covered today. We started by explaining the Fiat-Shamir transform and defining what a public coin interactive proof system is. Then we looked at the Schnorr protocol, which is an example of an interactive public coin proof system used to prove a single specific relation. Using Schnorr, we saw how to apply Fiat-Shamir to turn an interactive proof into a non-interactive one. This is exactly the workflow we'll follow with more advanced proof systems in the future, the ones that can prove arbitrarily complex statements. We'll first design an interactive proof system that is complete, sound, succinct, and public coin. Then applying Fiat-Shamir will turn it into a non-interactive proof. If our interactive proof system is not zero knowledge, we'll get a SNARK. If it is zero knowledge, then we get a zkSNARK. Thanks for watching, and I'll see you next time.